Hi, guys. Okay. Are you ready to think like a scientist? Here we go. What seems impossible about the idea of instant freeze water? What could be like a stumbling or an obstacle to instant freeze water? Why does it seem impossible? And here's just a fun little movie clip. This is not real. Okay, so instant freeze. Keep that in mind. Let's think about our vocabulary. Have we learned about the terms particle motion and molecules? What do you know about how they're connected? And take a look at the image. This will give you some ideas of some things we've already learned. Okay, notice the difference in temperature and the difference in particle motion. Remember, temperature is the measure of average kinetic energy of the particles in a system. The question we're going to be studying, what can have an effect on phase changes like freezing? You might have some ideas, but there might be some new things too. For example, in freezing, notice we're going from the liquid phase to the solid. The particles are getting closer and slowing down. Let's take a look at a phenomenon. You might have seen this. This was viral for a little while on social media like TikTok, Instagram, Snapchat, all those things. And you can try this at home. Now, it could be regular salt or the salt that you used on to de-ice your sidewalks. That would also work. Watch closely. Watch again. Okay. So think about that demonstration, that phenomenon. What kind of data would a scientist collect and how would they collect it? Again, what kind of data would a scientist collect if they were doing that experiment? And what data do they not need to collect? If you need to, pause the video. Hi, so we've just taken a look at that instant freeze water experiment. And we're going to take a look at it from another angle. We're going to explore like a scientist. Our two questions are, what effect does the salt have on the ice in the bucket? And what effect does the salt have on the water in the bottle? Okay. So instead of studying a bottle of water that's going to instantly freeze, we're going to take a look at an ice cream mixture and see if it freezes and what the salt's effect is on the ice. Okay, so you have the ingredients here. If you want to try this, you can pause the video and try this at home. And let's take a look at the experiment. Hi guys. Okay, so it's time to take a look at what's going on when you have salt and the ice together. Like in the instant freeze, they had the salt added to the ice to make that bottle instantly freeze. We're going to do an experiment here. We have the ice with salt and ice with no salt. And instead of using a water bottle to make the water freeze, we're going to have an ice cream mixture. Okay, so we're going to shake these for about 10 minutes each. And we're going to come back and see which one turns into ice cream and take their temperatures. So let's pause.
Yeah.
Okay, so we've been shaking for about 8 minutes. You can take a look and observe there are some differences already between the no salt and the salt. Okay, see, there's a lot more ice meltage in the one with the salt present. So let's pause and we're going to take some temperatures. Okay, so let's take a look at the no salt. Just observe, it's still very liquidy. And we're going to take a temperature reading of the cream mixture. It's about 39.4 Fahrenheit, which is above freezing, so it makes sense that it's still very liquidy. Okay, and again, you can see not a lot of the ice melted very much. Let's take a look at the one with the salt. We had a lot of ice melting. Okay, and you can see just by the texture, it's like a soft serve ice cream. And let's take a temperature reading. And this is 27.5 Fahrenheit, which is definitely below freezing, right? 32 degrees is freezing. So around 27 Fahrenheit is definitely freezing, and that makes sense because we have nice soft serve semi-solid ice cream. Again, if you want to try this at home, all you need is ice, some salt, little sugar, little half and half or whole milk, a little vanilla. Put them in a bag, shake it up for about 8 minutes with salt, and you get a nice soft serve ice cream. Okay, let's keep working on our experiment. Okay, so let's get ready to organize and analyze data like a scientist. We did an experiment with just ice and with ice and the salt, and we were trying to see what effect it had on the ice cream mixture inside. Well, with just ice and no salt, the ice didn't melt very much. And the ice cream mixture inside stayed liquidy, it didn't solidify. And its temperature was above normal freezing, 39 degrees Fahrenheit. With the ice cream mixture in the bag with the ice and the salt, you have a lot more ice melting. The ice cream mixture itself became a soft serve semi solid ice cream. And the temperature was much lower. Okay? It was below freezing at 27 degrees Fahrenheit. Okay, so how was this version of the experiment with the ice cream similar to the instant freeze water? Well, they both involve salt interfering with the ice's ability to freeze, causing the ice to steal or absorb energy. How are they different from the demonstration of the instant freeze water? Well, in the instant water freeze, the salty ice absorbed energy from the water in the bottle. And then when you tapped it, it froze instantly. In the ice cream experiment, the salty ice absorbed energy from the cream mixture in the baggie, turning it into ice cream. Let's keep going and gather some facts. Let's answer a riddle. I'm needed for life. When I get too hot, you can't see me. And I'm so mighty, I can make valleys. What am I? Water. Liquid water is needed for living things to survive. When heat is added, it evaporates. When it's frozen into glaciers, it can carve out valleys. But water can only do these things when there is a change in thermal energy. Okay, whether you're removing energy or increasing energy, different states of matter have different particle motion. For example, in a gas, particles move quickly and in all directions, making little contact with each other because they're so far apart. In the liquid, particles slide past each other easily. In a solid, particles stay basically in the same position but still move and vibrate. Now, this is going to sound weird, but there's no such thing as cold. Cold is really the removal or absence of heat. When you remove enough energy for a liquid to slow down and come together to be in the solid phase, then you have reached the freezing point temperature. Similarly, when you add enough energy for a liquid to speed up and spread out to be in the gas phase, then you have reached the boiling point temperature. Water's standard freezing point is 0 degrees Celsius or 32 degrees Fahrenheit. When this temperature is reached, the liquid molecules slow down until hydrogen bonds form the structures that cause ice, solid water. But if you add salt to the water confuses all of those bonds, and the temperature needed to freeze changes. You have to remove more energy to get those particles to slow down. This is called freezing point depression. It means water can be liquid even below freezing, below 32 degrees Fahrenheit or 0 Celsius. So let's think like a scientist about the instant water experiment. When water is super cooled below 30 degrees, it is barely hanging on to its liquid state. One small jostle or slight imperfection in the container will trigger the particles to line up suddenly and form a solid, like when it was hit on the table. And the ice cream experiment. Well, salt was added to the ice in the outer bag to force that ice to absorb or steal energy away from the ice cream mixture inside the smaller bag. When the ice cream mixture loses its energy, it starts to slow down and becomes more solid. So let's put all of this together. If you just have water or ice, right, it can melt pretty easily. However, if I have the salt, interfering with that process, you have to remove far more energy. In fact, the temperature has to be much, much lower than freezing in order for it to solidify. So it starts stealing energy from its surroundings and melting. In the instant water freeze bottle experiment, we have the water bottle, and outside in the bucket was the ice and the salt. Heat was traveling from the water bottle to the ice and the salt. The ice salt, again, was stealing energy from the water bottle. And when you took it out and tapped it on the table, it froze. In the ice cream mixture, again, we had the ice and salt on the outside in the large bag and the cream mixture on the inside. The salt, again, is lowering the freezing point for the ice and forcing this ice to absorb energy or steal it from the ice cream mixture. Since the ice cream mixture is losing energy, it starts to solidify and turn into ice cream. Now it's your turn to write like a scientist. In the winter, people add antifreeze to the water in their car engine. Antifreeze is a solute which gets added to water to make a solution. Adding pure antifreeze would not work, and your car engine would freeze up. But adding a mixture of the antifreeze to the water does work and helps keep your car running even on super cold days. Explain how the antifreeze is like the salt. Explain what antifreeze is doing to the freezing point of the ice water. And when the ice melts or steals energy, where is it stealing it from as far as your car engine is concerned? Try to put everything together. You can do it.